Hey guys, today we're going to talk about both regular hexagons and squares and some special properties that exist in them. So we'll start off with hexagons, and we've worked with some of these in the past. We'll just go into some of the special properties. I think I've mentioned them in some of the past videos. But let's say here's a kind of regular hexagon. We'll have to use our imagination. This hexagon, we'll say, is regular. If you are to one of the special properties, take the center of that. If you draw all the radii in, I think I mentioned this before, but if I didn't, then we'll mention it now. The central angles in here, each one of these, it's going to be, well, since there's 6 of them, it's going to be 360 divided by 6. So each one of these angles is 60 degrees. And which is nice. So we have all these angles are congruent, they're all 60. But if you remember, or if you know from a regular hexagon, their interior angles are 120, and since you're going to be dividing them in two, all these angles are actually going to be 60 degrees. Which means we create, when we draw all these in, we create not just isosceles triangles, but equilateral triangles. So in a regular hexagon, you're going to create 6 equilateral triangles, which is a really nice thing to know. That means the relationship between the radius and the side is that they are equal to one another. Now if you take one of these equilateral triangles, and for the sake of this, it's like radius, radius, and the side, which are equal to each other, but I'll just label it like that. If you draw that apothem right here. Well, one special part about this, actually I'm going to draw it a little bit bigger. Radius, radius, and side. If we draw this apothem we're going to have a 90-degree angle. You're going to create 30, 60, 90s. So these would be your 60s. These would be your 30s up here. So you'll create two 30, 60, 90 triangles, which is nice. And if you want to look for the relationship between the apothem and the sides, well, let's see. The apothem is going to be equal to 1/2 the side times the square root of 3. Because of that 30, 60, 90, remember this is going to be half and this is going to be the other half of the side. And if you were to take this and you were to substitute on into our general formula for area, 1/2, instead of the apothem you put times 1/2 side times radical 3, and then we would multiply by the perimeter, but for a hexagon it would be 6 times the sides. If you simplify all this, you're going to end up in the numerator with, we're going to have 4 in the denominator, 6 in the numerator, so a 3 in the numerator, 2 in the denominator, and then you'll have root 3, and side times side is side squared. So this little formula would get you the area of a hexagon in terms of the side. So if you know one side of the hexagon, you square it and then multiply by square root of 3 and 3/2, and you would get the area of the hexagon. So those are some of the special things you can use when working with regular hexagons. It's nice to know these little bits of information, the relationships between like the radius and the side, things like that. Now we're going to work into some of the special relationships with squares or a regular quadrilateral. So in a square, that's a decent-ish square. In a square, let's say we know the side length, and we draw in our radii. When you draw these in, your 4 central angles, well, they're all going to end up being right angles. 360 divided by 4. So when you draw that, you're going to end up making 45, 45, 90s. These are going to be 45s. All these marked congruent. And it's also true because they're going to be isosceles, so 45, 45, 90s. Obviously, to find the area of a square, you could just do the side squared. That shouldn't be too hard to figure out. But if we look into now drawing that apothem to investigate a little further, when you draw that in, you're going to create like a smaller 45, 45, 90. So it would look like this. You're going to know this is A, and these are your 45-degree angles. This little triangle right here, you've kind of taken and put right here. And this little length on the bottom, well, this would be 1/2 the side. So the relationship between the apothem and the side is that 2 times the apothem equals the side, or 1/2 the side equals the apothem. And if you're trying to find the area and you only know this value here, you only know the apothem, then you could just substitute in. The area is the side squared. So the area, you could just say, is 2 times the apothem, that quantity squared, or 4 times the apothem squared. So if you only know the apothem, you can use that to find the area as well. Another cool relationship with squares, I don't know if we talked about this in the past, it doesn't have to deal with these little triangles, it has to deal with the diagonals in the square. I don't know if we've talked about it, so I'll just mention it now. Let's say we have, we'll leave those up. Say we have a square, and if you're looking at the diagonals of a square, the relationship between the diagonal and the sides, here's a side, here's a side, here's a diagonal. The diagonal is going to be equal to the side times square root of 2, and that means the diagonal over the square root of 2 is equal to the side. I'm going to leave it like this for now, because we know the area of a square is the side squared, so that means the area is also equal to diagonal over the square root of 2 squared, which is simply diagonal squared over 2, which you can say is 1/2 times the diagonal squared. So if you know the diagonal of a square, you also can find the area. You square it and take half of whatever the square is. And just like that, we have some new formulas, some new relationships that exist. I think it's fun to look into different relationships between parts of geometric shapes. All right, that's all we have for the day. Have a good day, guys.